Okay, so second lesson, auxiliary angle method. We're going to be solving equations that are in the form sine x plus cos y or sine x plus cos x, those kinds of things. The first couple of questions, we're not actually going to be solving them yet. We just need to get used to trying to put them into the right form so that we can solve them. And these do come from our compound angle formulas, all these rules that you see here. So you'll probably find that you don't need to memorize them, these ones in here. There is some shortcut methods that can be used to help you with these if you're watching other videos or things around. I don't recommend that you adopt the shortcut methods though, because it's easy to fall for traps of when the angles that we're going to be finding aren't acute. Or the shortcuts tend to go, let's find the acute angle, and if it's not in the right form, it's actually not an acute angle that you're meant to be finding. Okay, so the method I'm going to show you hopefully will be one that will work for everything and we won't fall for any silly traps that they try to throw at us. I am, I believe. Yes, now I am. Okay, so what we're going to be doing is we want to take an equation like this one here, y is equal to sine x plus cos x, and I will need to rewrite it because I don't like to solve an equation that has sine and cos in it, right? I want to rewrite it into a form like that. Okay, it's either going to be r sine x plus alpha or cos x plus alpha. There'll always be an r, and there will be alpha represents some angle that we're going to need to find. So what we want to start by doing is start with the r sine x plus alpha, and let's do an expansion. Careful, how do you expand sine x plus alpha using your compound angles?
2 sine x cos
It's not a double angle.
Sine x plus cos alpha.
So let's leave the r there. Sine x cos alpha, yes? Yeah, good. So that is a compound angle expansion that's on your formula sheet. Let's expand the r through as well now. So r sine x cos alpha plus r sine alpha cos x. Okay, now what we are actually doing though, that r sine x plus alpha is actually representing the y equals sine x plus cos x equation that we're wanting to potentially eventually solve here, right? So I'm going to change that to be sine x plus cos x is equal to the r, or that whole big expansion again. Okay, what we're going to do is we're going to equate the coefficients of the ones with the same pronumeral in them. So for example, sine x. There's my sine x, and over here is my sine x. What is the coefficient of the sine x on the left? Yeah, so I'm going to write a little note here so you remember what I'm doing. I'm going to write equating coefficients. You wouldn't normally do this, but just if you're looking back at your notes, you might want to know that. So on the left, we have a 1. On the right, what is the coefficient of the sine x? Yes. Okay, now let's do the same thing for the cos x. What is the coefficient of the cos x on the left? Left first. 1 again. And on the right, r sine alpha. Does that make sense? Sammy, you all right with that?
So it's the sine x and the r sine x.
Yeah. So I've highlighted them. So if I do the pink ones there, so the cos x. Which one first, sorry? It doesn't actually matter which equation you write first. You just have to have both of them. Because what I've made is two equations that have r and alpha in them, which are technically simultaneous equations, but you do have to be careful how you solve them so that you don't, because they're angles, you don't want to mess with your solutions. So what you need to do from here, this is going to be equation 1, this one's going to be equation 2. We're going to do a cool little technique that we don't normally do with simultaneous equations. We are going to square both of the equations and add them together. Okay, so we're going to do 1 squared plus 2 squared. That means I'm going to have to do, for the ones that are in there, I'm going to have to do 1 squared plus 1 squared. They're both the left-hand sides of both of those equations, right? And then the right-hand sides of both of those equations, I'm going to have to go r squared cos squared alpha plus r squared sine squared alpha. Now, why have I done this? Because I have now made a sine squared plus cos squared on that right-hand side. If I factorize the r squared out of it, that will just disappear because it's equal to 1. So I will get 1 squared plus 1 squared, which is 2. I factorize the r squared out, and the sine squared plus cos squared disappears. Is that okay if I just don't write that down? All right, cool. Then I can get r. R is going to be equal to the square root of 2. Now, I'm not plus or minusing that because it does say up here that r has to be positive. Okay, so it's just a positive square root of 2. Okay, so we've found r, but I still need to find the alpha. To do that, I'm going to go back to my equation 1 and 2 again, and I'm going to divide equation 1 by equation 2. Okay, that's because, equation 2 by equation 1, sorry, I said the wrong way around. That's because sine divided by cos is going to make tan, one of our lovely favourite things. So let's write down what we get when we divide those. 1 divided by 1 for the ones that are on the left, and then we have r sine alpha over r cos alpha, dividing my equation. So 1 divided by 1 is 1. The r's will cancel out, and sine over cos is tan. So I have tan alpha is equal to 1. Now, what value of alpha, tan of what, gives 1? Pi over 4, so you could either do it as 45 degrees, or even better was to go straight to radians. Good job, pi over 4. I know it's in radians because the question told me I needed it between 0 and 2 pi. So I've done what I need to do. Let's just rewrite out our solution. We were asked to write sine x plus cos x is equal to r sine x plus alpha. We just want to sub in the x and the alpha that we've found. So r was root 2 sine of x, and my alpha was a pi over 4.
Couldn't it be on 5 pi over 4 as well?
Because you've moved it along.
In the other positive 10.
Yeah, because you've got all those different phases. Yes, you could move it different places. Yes, be careful of that. Just, we are going to find, let's do the next one because you'll see what I mean. We are going to find ones that aren't acute angles, yes. So, part B, express y equals sine x plus cos x in the form r equals cos x plus alpha. Okay, so this is the same wording of the question, so we're going to be doing the exact same process. Let's set it up again. Start with the r cos x plus alpha. Expand it out. This is a cos expansion. Who wants to try this one? Nope. Yep. Yes, it's cos x. Yes, good. It's coming back to you. Okay. Expand the r through. It's going to be half the topic, yeah.
very rarely.
Okay, so I've also, like I did last time, instead of writing r cos, I've put that back to be sine x cos x, because that was what my y equals equation was, so that I can equate my coefficients. So, coefficients, let's start with the sine x. There's the sine x and there's the sine x. So on the left, I have a coefficient of 1. On the right, I have a coefficient of, be careful.
Minus r.
Yes. That minus is important because it's telling me that the sign is negative, which means I'm no longer in the first quadrant. My alpha that I'm going to be solving for will not be an acute angle. Okay? All right. Second one. Cos alpha, cos alpha. Coefficient on the left is a 1. Coefficient on the right is... Yes. Oh, I highlighted the wrong one, but you know what I mean. Let me fix that. I highlighted the alpha instead of the... There we go. Should have been the cos x that I was highlighting. Okay, so equation 1 and equation 2. Let's do our method. First thing we're going to do is to square them and add them. So equation 1 squared plus equation 2 squared equals 1 squared plus 1 squared plus the negative r squared is going to become positive r squared sine squared alpha and r squared cos squared alpha. You guys okay with you seeing what I'm doing there? Okay, factorize the r squared out, which means the sine squared plus cos squared would just become a 1. And we're back to our 2 again. So we're still getting r is equal to root 2 like we did last time. Okay, but this is the different part. When we do our second bit, which one am I dividing by which one? I'm going to do equation 1 divided by equation 2 so that it's sine over cos. So it would be negative r sine alpha over r cos alpha equals 1 over 1, which is just 1. Now it's important here that you make yourself a little note that you know that the sine is negative, the cos was positive, and that's telling me what quadrant my alpha has to be in. What quadrant is sine negative but cos is positive in? The fourth. So I'm looking for a solution in the fourth quadrant. The r's will cancel off, and I will have negative tan alpha equals 1. Move the 1 across, the minus across. Make negative 1. So we know that tan of 45 is 1. If it's in the fourth quadrant, yes.
So this is when we're not finding this.
Yes, correct. Okay, so that's it. We've actually done it. Let's just rewrite it out. So it's going to be sine x plus cos x is equal to root 2 cos x plus 7 pi over 4. Now those two questions, part A and part B, it was the exact same starting equation, y equals sine x plus cos x, but it was because one of them we were changing into sine and the other one we were changing into cos that it meant that it affected the value of the alpha. R didn't change, but alpha did. So just be careful of that. Part C, we want to sketch the curve showing all intercepts and turning points in the interval between 0 and 2 pi. They are effectively the same equation, just with a phase difference. I probably think the first equation might be a little bit nicer to move because we've got to draw it. So the first equation was y equals sine x plus cos x, that was our thing, which was equal to root 2 sine x plus pi over 4. So that was when we changed it into sine. What do we know about that equation? The root 2 is amplitude. What does that pi over 4 tell us?
Period is shifted.
Yes?
Pi on 4 to the left.
It's actually shifted to the right, but the intercept is minus pi over 4, is what you're thinking. So I think you're thinking the right thing, but it's when you word it, that's all. So it's shifted right pi over 4, or in other words, the intercept has been moved to negative pi over 4 from 0. Okay, so let's see if we can draw it. We're going from 0 to 2 pi, so let's put a few little increments in here. That pi over 4 shift means it would be good if I had little pi over 4s, it's going to be easy just to move things across one spot. So pi over 2 there, pi over 4.
Should that be?
That should be a 4, yeah, I think I just saw that too. 4 pi over 4, 5 pi over 4, 6 pi over 4, and 7 pi over 4. Okay, we're not reflecting or moving anything up or down, so this will be a little bit easier than the last one that we did. It is a sine curve, which normally starts at the origin, right? And I am shifting it to the right pi over 4, or the intercept, as I said, the other way of phrasing that would mean that no, I think you're right. It is. Am I getting my words around the right way or left? My intercept is at minus pi over 4. So it should be over here. I have moved left. Left. It was left.
What's the same with
It works the same on the graph. Okay. So from the origin, I've gone to minus pi over 4, but that's actually off. I don't need to draw over there, but it might be good as a little starting point, even though it's not part of where I need to draw. Going 90 degrees over, we would normally be at pi over 2, but we're coming one space in, would be at pi over 4. Where will that be? All right, sorry, let me rephrase. So normally for sine, we have 0, our 0, then our pi over 2, pi, 3 pi over 2, and 2 pi, right? So I want to take each of those 4 key points and move them over pi over 4 to the left. Okay, so I've taken my 0 and I've moved that over to minus pi over 4. The pi over 2, which is normally at 1, I'm going to move that across to be at pi over 4. But what's the amplitude of this graph? It's root 2, it's not at 1. So I'm going to make this a root 2 here. And instead of it being at pi over 2, I'm going to move that across one spot to be at pi over 4. Yeah? Then pi is back down to 0, but I need to move it across a quarter to there. And 3 pi on 2 is normally down at -1 or negative root 2 for us, since our change of amplitude, but move it across one spot would be at 5 pi on 4. So that's going to be down here at negative root 2. And finally, the pi over 2, which is back at 0, move it over pi over 4, so it's 7 pi over 4 will be my intercept there. Do you see what I've done? I've just taken each point and just slid everything across one spot. So I would like to have an intercept though. Could I find my intercept over here? What happens if I sub in when x is equal to 0? When x equals 0, I would get y equals root 2 sine of pi on 4, which is 1. Yeah. So that intercept right here below the root 2, that would be an intercept going through 1 there. So let's draw. From the 1, we're going to come up a bit, down through the 3 pi on 4. And I do technically need to go a little bit I need to go to pi on 2. Where do you think it's going to be at pi on 2? Back up to the 1 again. The symmetry of it all. Okay? And there would be my curve. All right, next one. Question 2. Do it all again. Express y equals 3 sine x minus 4 cos x in the form r cos x minus alpha, where r is greater than 0. And we're doing this one in degrees. It says between 0 and 360. Give your answer to alpha to the nearest degree. Okay, so we've practiced this now. We know how to do this. All right, so let's change our 3 sine x minus 4 cos x by expanding that, the r cos x minus alpha. Okay, expanding cos with the compound angle would be cos x cos alpha. Because it's a minus, yes, it becomes a plus. Good. Sine x sine alpha, close bracket. Expand the r through. Okay, we equate our coefficients. So on the left-hand side, I have a sine x there and a sine x there. So that would be a coefficient of 3 on the left and r sine alpha on the right. That's going to be equation number 1. My cos x on the left has a negative 4, so warning signs with minus signs means we're moving out of the first quadrant. And that's going to be r cos alpha for the right-hand side of the equation. So that's equation 2. To solve them, we sum and square. So 1 squared plus 2 squared is going to be 3 squared plus negative 4 squared. I don't actually need the minus because it'll become positive anyway. And r squared sine squared alpha plus r squared cos squared alpha. Okay, 3 squared plus 4 squared makes 25. Factorize the r squared out and the sine squared plus cos squared disappears. Square root the r to find that r is 25. Next, sorry, what's that, Sunny? Yeah, positive 5 because we squared. The negative will come up in the next one. Now we want to divide our equations. Remember, you want sine on top. So that will be equation 1 divided by equation 2. Oh no. So that will be r sine alpha over r cos alpha equals 3 over negative 4. And make a little note here, what's happening with our minus signs. The sine is positive this time, but it's the cos that's negative. Which quadrant does that work in? That's right, therefore second quadrant. The r's will cancel out and we get tan alpha equals negative 3 over 4. You will need to do this in your calculator because it's not an exact value. to the nearest degree, what did you get? Yeah. So it automatically went to the second quadrant, right? You didn't have to find it. You went to the second quadrant? You didn't have to, yeah, so you did put it in there. You found the acute angle first and then subtract, yeah. Yeah, cool. So you had to put it into the second quadrant. Good, and then we just have to rewrite that out in the right form. You right, Sunny?
Oh yeah, we can just get that.
Yeah, minus it from 180 so that's in the second quadrant. Is it? It is? Okay. Oops.
So R is always the square root of the 2 told me to add.
Yeah. So that one is pretty much a given. That's a shortcut that you can always use, but it's about that angle. Because if you get that angle wrong, because it's in the wrong quadrant, you're in problems. Okay, we want to draw this, and then there's a part C where we actually finally get to do the solve. Oh, no, it's not. Oh, that's a different.
Next one's.
Yeah, the next one's a solve. Sketch the curve showing correct to the nearest degree all intercepts and turning points in the interval between minus 180 and 180. Now, what do we know about this graph? We know that the amplitude is a 5. We know that that minus 143 is moving my graph. Right 143. Oh, good. Let's do it then.
What is this? Oh, 95% now you're actually getting it.
I'm actually getting charged. Okay, we need this graph for the other questions, I think, so make it a reasonable one. Okay, I'm going to show 90 and 180 and negative 90 and negative 180 for a start. The amplitude is 5 and negative 5. 1, 2, 3. Okay, this is a cos graph. So cos normally starts at 0, 1. So from the origin, it starts at 1, which in this case would be 5 because we've times it by 5. But we have moved it 143 places to the right, which means at about here, there's going to be my 143. That is where the starting point of my curve is. Okay? If I go backwards 90 degrees, I need to come down 2.5. Actually, let's go full 180. Let's go all the way to the other end. So let's take 180 off 143, which you get. So at negative 37 degrees, where will my curve be at? No, negative 5. I went the full 180. Yeah, so I missed the 90 in between. We could, because it's not going to be a nice intercept. So in between there, which would be at, what is 30? So we've got 90, 143 minus the 90. So that's the 53. So at 53 in here, that's where it's going to go through, because that would be the middle point. Then let's subtract another 90 off that 37. So we've got negative 37, so take another 90 off. We're at negative 127. Would be my next intercept up here. Yeah, but that's past where I need to be. I need to go to negative 180. So I do need to find, because I've got a curve that's coming like this. Okay, I've kind of got most of it, but I know that my curve needs to I need to finish it to the 180 and the negative 180. I need to sub one of them in. So let's sub in when x is 180. And we would get 5 cos 180 minus 143, which makes 5 cos 37, type that in, makes a 4. All those yucky numbers, and it comes out with a very nice little 4. So it actually comes back down. Yeah, but you know, there you go. So 4, and then on the negative 180, because it's symmetrical, it will also be back up here at 4. So we can, that's not the top, don't make that look like a turning point up there. It would keep going a little bit further, and this one will come back down to here. Yeah? Okay. Are we going to make it? Maybe. Question 3. Solve 3 sine x minus 4 cos x equals minus 2 between minus 180 and 180. So that is our equation, right? That is the same equation we've been doing, but we're now saying that it's equal to minus 2. So I'm not going to do the whole find the r and the theta. We've already done all of that. We know that the 3 sine x minus 4 cos x, we have already done the work, and we know that that's equal to 5 cos x minus 143 degrees. Okay, that's what we found in the last question. But now I know that I want that to be equal to negative 2. Don't use the sine x minus cos x side. We're trying to get rid of that. That was the complicated side. We want to take the 5 cos x minus 143, and we make that equal to negative 2. And we only got one trig function in there, so we can solve that and find out what the x is. So we divide the 5 away. So that's negative 2 over 5. It says to the nearest degree, so inverse cos of 2 over 5. If you leave the minus sign out of it, you'll just be finding the reference angle. Do you want me to tell you what it is? It's 66 degrees. Which quadrants should I be getting solutions in? Yes, 2 and 3. But be careful, it's going to be 66 degrees for our reference angle. Wait, we're solving between minus 180 and 180 though. So we actually have to go backwards in the bottom half of my all stations to central. Yeah? So the x minus 143 would be equal to 114 in the second quadrant, because 180 minus the 66, or it's negative 114 for the one going this way, because we're coming backwards. Yeah, remember doing that before? Then just move the 143 degrees across to the other side, and I would get 257 or 29 degrees. But then I've gone out of my range again, haven't I? So what do you think I should do with that 257? Not kill it. Is there an equivalent one that is in my range? I would subtract 360 off it. Yeah. So it's a negative 103. Okay, we are actually kind of done, because part B is just saying, hence, from the example in question 2, solve your same equation again, equals minus 2 between minus 180 and 180. So if we looked back at this diagram here, and we very carefully drew a line at -2. These solutions, which mine doesn't look overly accurate, I have to be honest, but those solutions should be the two that we've just found. So the one just past that should be past the -90, obviously needs to be -103. And the other one needs to be 29. Yours is past the 90. Great. Yours is excellent. So yeah, yours is a bit more accurate. So that's just confirming we've done it graphically. You can see that the solutions are reasonable, and we've also done it with the calculations. So let's just write in there our solution again. Our solution, there is one other little difference here. It says to solve for where it is less than -2. So where is it? Less than is going to be, that's right, that part in there. So to be greater than the 103, but less than the 29.